Look around your room for 10 seconds and count what contains plastic. Your phone case, keyboard, charging cable insulation, water bottle cap, food packaging, chair parts, paint binders, maybe even fabrics in your clothing. Plastic is so common that it feels almost invisible, like air or concrete. But that invisibility is exactly what makes it hard to discuss clearly. People often treat plastic as one thing, as if all items made from it have the same value and impact. They do not. Plastic is a family of materials built from polymers, long molecular chains that can be engineered for very different outcomes. Some are rigid and structural, some are flexible and film-like, some handle heat, some resist chemicals, and some are designed for contact with food or medicine. That versatility is why plastic became deeply embedded in modern life. The same core concept can become a pipe that lasts decades, a sterile medical component, or a wrapper used for minutes. So the real story is not just that plastic is everywhere. The real story is that one material platform now serves countless functions across the global economy, and we are still learning how to live responsibly with the scale of that success. At its core, plastic means a material that can be shaped under heat or pressure into stable forms. That moldability changed manufacturing forever. Before plastics became widespread, many products depended on heavier, scarcer, or less adaptable materials like metal, glass, wood, or natural fibers. Those materials still matter, but plastics offered a new design freedom, complex shapes at high volume, with lower weight and often lower cost. That combination enabled mass production to accelerate in consumer goods, transportation, electronics, and construction. Engineers could reduce part counts, simplify assembly, and integrate functions into a single molded component. For households, this translated into cheaper access to products that were previously expensive or fragile. For industry, it reduced logistics costs because lighter materials are cheaper to ship. For public health, single-use sterile products became easier to deploy consistently. This matters because the plastic debate often starts at pollution, which is crucial, but if we skip the reasons plastic won adoption in the first place, we miss the full picture. Plastic spread because it solved real problems very efficiently. The challenge now is that the same properties that made it useful, especially durability and resistance to degradation, also make waste difficult to absorb in natural systems. The growth numbers reveal just how quickly this material moved from innovation to planetary-scale infrastructure. Global plastic production is estimated at around 9.2 billion metric tons between 1950 and 2017, and more than half of that total was produced after 2004. That means we did not just adopt plastic, we accelerated into it. In 2023, global annual production was already above 400 million metric tons, and if demand trends continue, annual output could exceed 1.3 billion tons by 2060. Those are not abstract statistics. They describe extraction, refining, manufacturing, logistics, consumption, and disposal systems that now run continuously in every region. Plastic demand tracks urbanization, rising incomes, retail expansion, and modern supply chains. As economies scale, packaging demand typically rises because goods travel farther, shelf life expectations increase, and distribution becomes more fragmented. Construction demand also rises, especially for piping and insulation in growing cities. So production growth reflects development patterns as much as consumer preference. Still, exponential growth creates a structural pressure point. Even if waste management improves, the total volume entering the system can outpace collection, sorting, and treatment capacity. In other words, we are not only managing existing plastic better or worse. We are constantly feeding a larger flow into the pipeline. To understand impact, we have to follow where plastic is used. Packaging accounts for roughly 40% of total use globally, while building and construction accounts for about 20%. The packaging share is especially important because many packaging formats are used briefly, then discarded quickly. A bottle may be consumed in hours, a wrapper in minutes, a shipping film in days. By contrast, construction plastics like PVC pipes can remain in service for decades. So two plastic items can have totally different waste timelines even if they weigh the same. In developed economies, plastic use is often split heavily between packaging and buildings, while developing economies may lean even more into packaging as consumption and distribution systems expand. One cited case is India, where packaging represented about 42% of consumption. This is why policy and design decisions cannot treat all plastic applications equally. A medical device, a water infrastructure component, and a disposable snack wrapper have different risk profiles, replacement options, and social value. Serious solutions prioritize by function and lifespan. The central question is not simply, can we use less plastic everywhere? The better question is, where is plastic essential, where is it merely convenient, and where can redesign cut waste without creating new problems? A lot of discussions frame plastic as a modern mistake, but history shows a more nuanced path. The first fully synthetic plastic, Bakelite, was invented in 1907 by Leo Baekeland in New York. That moment marked a shift from relying mainly on naturally occurring materials to designing molecular behavior intentionally. Over time, many plastic families emerged, each tuned for specific performance needs. Polyethylene became dominant in packaging due to flexibility, processability, and low cost. PVC became central in construction and piping because of durability and chemical resistance. Other plastics support automotive parts, furniture, toys, and countless industrial applications. Behind these products was a century of polymer science, driven by chemists and physicists who built the theory and process control needed for mass adoption. So when people ask, why did plastic take over, the answer is not just marketing or convenience culture. It is also scientific capability converging with industrial demand. We learned how to build materials that could be tailored faster and cheaper than many alternatives. That same success now creates a responsibility gap. Our production and design systems advanced faster than our end-of-life systems. We became excellent at making plastic, but much less effective at deciding what should happen after first use. One reason plastic remains hard to replace is that it delivers genuine public benefits when used well. Consider water and sewage infrastructure. In many countries, resilient piping materials such as PVC support sanitation systems that reduce disease and improve daily life at massive scale. In healthcare, plastic allows sterile, lightweight, and precise devices that are practical to produce and distribute. In transportation, replacing heavier components with plastics can reduce fuel use and emissions over product lifetimes, depending on application and design. In construction, certain plastic components resist corrosion and moisture in ways that extend service life. Even food systems depend on packaging that protects products from contamination and spoilage during long distribution chains. None of this erases waste problems, but it explains why blanket narratives fail. If we remove plastic without function-by-function replacements, costs can rise, access can drop, and other environmental burdens can increase, for example through heavier transport materials or higher food waste. Effective policy must separate high-value, hard-to-substitute uses from low-value, avoidable uses. It also needs life cycle thinking, extraction, manufacturing, use phase, and disposal. A material that looks bad at disposal might still reduce harm elsewhere, and vice versa. Real progress depends on seeing the full system, not just one stage. Now the difficult part, what happens after use? Most plastic waste management systems were not designed for today's scale and complexity. Plastics come in many resin types, additive packages, colors, and composite formats, which makes sorting and reprocessing difficult. A multi-layer package that performs brilliantly for shelf life can be nearly impossible to recycle economically. Contamination from food residues, labels, adhesives, and mixed materials lowers recovery quality. Collection systems vary sharply by region, and even where collection exists, downstream processing capacity can be limited. This is why global outcomes remain weak compared with production volume. Of all plastic discarded so far, only a small fraction has been recycled, while a larger share has been incinerated, and substantial amounts have gone to landfills or leaked into the environment. Recycling is important, but it is not a magic endpoint. It can be constrained by economics, quality degradation, and market demand for recycled outputs. Some products are not realistically reusable or recyclable in current systems. So when a package carries a recycling symbol, that often indicates potential compatibility, not guaranteed recovery in your local context. The gap between technical possibility and real-world execution is one of the defining challenges of the plastic era. Leakage into nature turns a waste management problem into an ecological one. Plastics degrade slowly, and instead of disappearing quickly, many items fragment into smaller particles over time. These microplastics can move through waterways, soils, air, and food webs. Marine environments receive special attention because visible debris accumulates in coastlines and ocean gyres, forming garbage patches that symbolize a broader systemic failure upstream. But marine pollution is not only an ocean story, it often begins inland through inadequate collection, open dumping, stormwater transport, and river systems. Microplastics are concerning not just because they exist, but because they persist, travel, and interact with organisms at scales difficult to monitor and remediate. Once widely dispersed, cleanup becomes expensive and incomplete. That means prevention is usually more effective than downstream recovery. It is easier to stop 1 ton from leaking than to remove that ton after fragmentation and distribution. This prevention logic shifts focus toward product design, waste capture, and infrastructure investment rather than relying mainly on volunteer cleanup optics. Cleanup still matters for habitats and awareness, but long-term impact comes from reducing leakage pathways at source and improving material stewardship across the full chain. A common question is whether bioplastics or renewable feedstocks will solve everything. The honest answer is partial, context-dependent improvement, not universal replacement. Most plastics today still come from petroleum and natural gas, though a growing minority uses renewable inputs like polylactic acid. Feedstock shifts can reduce dependence on fossil sources, but they do not automatically fix disposal outcomes. A plastic made from renewable carbon can still become pollution if mismanaged. Some alternative materials require specific industrial composting conditions that are unavailable in many places, leading to confusion and contamination in existing recycling streams. Others may have trade-offs in durability, moisture resistance, or cost. This does not mean alternatives are pointless. It means material transitions need infrastructure alignment, labeling clarity, and realistic use case targeting. The best question is not, what single miracle material replaces plastic? The better question is, which material fits which function with the lowest total harm in that context? For some uses, redesigning to eliminate unnecessary packaging may beat material substitution. For others, durable reusable formats may outperform both conventional and bio-based single-use items. Progress will likely come from a portfolio strategy, not one headline. Technology. So what does a credible path forward look like if we take both utility and harm seriously? First, reduce avoidable short-life plastics where alternatives are practical without shifting harm elsewhere. Second, design products for end-of-life reality, not idealized recovery. That means simpler materials, fewer incompatible layers, and clearer labeling tied to actual local systems. Third, expand collection and sorting infrastructure, especially in regions where leakage risk is highest. Fourth, build stronger markets for recycled resin so recovered material has reliable demand and price support. Fifth, treat long-life essential applications differently from disposable convenience applications in policy and procurement. Sixth, improve data transparency so companies and governments track real recovery outcomes, not just theoretical recyclability claims. Finally, align incentives across the chain. Producers, retailers, municipalities, and consumers should not operate as disconnected islands. The plastic age is not ending tomorrow, and pretending it can disappear instantly is not serious planning. But continuing business as usual is equally unrealistic. The practical objective is to keep the benefits that truly matter while shrinking the waste footprint year by year through design discipline, infrastructure investment, and smarter rules. Plastic built much of modern life. The next chapter is whether we can build modern responsibility at the same scale. If you found this helpful, please like this video and subscribe for more explainers.